Hello, my Theosophical Lodge buddies. This is Jeff Curtis coming to the SF Theosophical Lodge folks from the Sierra Foothills again. It's nice to be with you. I guess it was a couple months ago we did this last, towards the end of June. It's been an interesting summer, gotten a lot done. Um, and it's nice to have a chance to speak to you guys again about science. It's always kind of fun. What I want to do tonight is dovetail a little bit with what we did last time. I tend to do that. There's a certain amount of repetition. And then start taking it off in a new direction. So I think ahead of time I had advertised this talk as being more things about light. So last time we went through some of the history of our concept of light, the scientific concept of it. I haven't yet moved into more spiritual types ideas or philosophical interpretations of light, but we're going to get there. I'm sticking more with the scientific stuff to form a basis for us to have discussion. Um, we talked a little bit about the structure of light and how we think of it scientifically. Just a second here. Um, you might remember this diagram is sort of a cartoon of what a photon looks like. A photon being a package of light energy, as was surmised by Albert Einstein in his interpretation of the photoelectric effect. And we talked about the photoelectric effect last time. Um, what I want to remind us of right now, however, is sort of a different aspect of what I began to introduce last time, and it has to do with what light does, the role of light, and how we relate to it, experience it. And you might remember that I mentioned a little bit last time about some of the ancient Greek ideas about light and about seeing and perception. I'm just going to mention a couple of those things here again to refresh on it, because there were different schools of thought. It's very, very interesting to me that they were so far ahead of their time in a way, because they valued the power of pure thought and reason and discourse, and with relatively little experimental evidence or sophistication, they were able to reason their way to such impressive places. So there was one school of thought, Leucippus or Lysippus and Democritus, about 430 BC, where they were thinking of light as light and vision as having to do with tiny particles that were coming from some luminous body into the eye. So they sort of got it. And this is intuitively obvious. It's easy to see how they'd come by it, that there was something coming from objects into the eye. But then there was a deeper level of thinking. And Euclid, Plato, Socrates, they actually had a little different take on it, which is they included the idea of the eye sending filaments of something out to touch objects, which then somehow resulted in information being backscattered or felt, or it's unclear, uh, back to the eye. And so there was a reaching out and a receiving back involved in the act of seeing and perception with light. That is so interesting, because that's going to dovetail with one of the interpretations of quantum mechanics and the measurement problem that I'm going to get to here in a while, and we'll be ending on tonight. Um, just to be complete about this, there was also Empedocles in 500 BC, a while ago. He thought that he was a student of Pythagoras, and he thought that light was a wave-like phenomenon that had a finite travel time. Think about that. And that seeing somehow involved emissions from the object into the eye, but he had a few more ideas. I guess to some extent he was a precursor of the school of Sfts and Democritus. Amazing to me that he had intuited the wave-like nature of light and that it had a finite travel time. Impressive. So with that as a little bit of a recap, then I want to take us into another area we have discussed together in some depth, actually, which has to do with relativity and the nature of space-time. Because there are some interesting relationships here, and the nature of light, particularly the speed of light, ends up playing a central role in relativity and the construct of space-time and space-time intervals. And if you were to look back over the last few talks that I've shared with you, you would get some real details about that. So what I want to throw up for you here right now by way of review is to look at this picture. So what we see there is a space-time diagram. And along the vertical, or the y-axis, we have time in units of the speed of light. And then we've got distance, just one dimension of distance along the x and y axes. And we could think of that as displacement in one direction of x, say, along the right-hand side, or the opposite direction, along the left-hand side. That slope, that diagonal line, that represents the speed of light. So that would be distance per time, where distance horizontal, time is vertical, but we can still divide those by each other and get a maximum speed that our universe allows. And that speed is the speed of light, 300 million meters per second. A very fast speed, but is nonetheless quite measurable with modern apparatus. And that confirmed stuff that had been arrived at in 500 BC by ancient Greeks. That's great, huh? So let's think a little harder about some of the implications of this graph, because they are interesting. I'll show it again here. You note the line, the dashed line there, that, oops, there. The dashed line is what would happen if we had an object whose trajectory was only along the vertical at first. So if something is just stationary as far as we can tell, it's still moving along that vertical axis. And in fact, that is the fastest rate of motion through space-time that can happen. It's non-intuitive, but something sitting still to us in terms of its spatial velocity is actually moving through space-time at the maximum rate. That takes a little getting used to and digging into the math and getting comfortable with it. Well, what happens if we tip that and we make a trajectory that now involves motion through space? So we tip that trajectory through space-time over, and we're now acting on a particle. We're making its trajectory also include motion through space. A couple times ago, we went through sort of a proof using the definition of the space-time interval. And what we reasoned our way to was a result from, sometimes it's called the twin paradox. More generally, it's used as a way of showing people how it is that motion through space causes clock rates to change, or so-called proper time intervals. So one of the things that we defined and talked about in some detail over the last few meetings is this idea of a space-time interval. So you see where it says delta S being equal to the speed of light squared times delta T. that being the time between two events, squared, minus delta x squared, where delta x is the distance between 2 points, or 2 events, actually, is how it's usually presented. Deep considerations of that space-time interval, and we went through this in a more detailed way a few months ago. What it leads us to is a few simple equations. So using the definition of space-time interval and a few assumptions, we can show these 3 results that I've written down for you here. So delta tau, that's referring to the clock rate, or proper time, or the rate of proper time passage of some particle that's moving. Therefore, relative to us, it has a different rate of passage of time. So we're gonna distinguish between the proper time of a moving whatever it is relative to us, and we're going to pretend we're stationary. We're actually not. We're moving through time at some high velocity, and in truth, the Earth is moving. But let's just not sweat that right now. Well, you can show that the clock rate, delta tau, the rate of passage of proper time for some object that's moving, will be equal to delta t, that's the laboratory frame rate of time passing, divided by quantity gamma, where gamma is something called a Lorentz coefficient. That Lorentz coefficient is one of the fundamental quantities of relativity theory. That gamma is equal to 1 over square root of 1 minus that quantity you see there, which is the velocity of motion of something divided by the speed of light squared. So this shows up all over the place in the math of relativity, that Lorentz coefficient. What this all means, if we boil it all down and think about it, it tells us that as the velocity of some moving particle that we're studying or measuring or what have you approaches the speed of light, that Lorentz coefficient goes to infinity. And since we are dividing by that gamma factor, it tells us that proper time, or the clock rate of a moving clock, asymptotically approaches 0 as its velocity, as judged by us, relative to us, approaches the speed of light. So I hope that's not a burdensome amount of algebra for you guys, but you know, it's not so bad to see stuff like this once in a while. All right, now here's where it gets kind of interesting, a little bit controversial. When you have an expression like this, the delta tau being equal to delta t over gamma, and gamma goes to infinity, where we end up with then is that time rate of the moving object, its clock rate goes to 0. More formally, we would say that it's undefined. And we can now at least conjecture about, or talk about in an asymptotically true way, what's life like for a photon? Okay, so photons are those things that are moving around and carrying energy. The photon, you could think of it as the unit of exchange of causality, because at the deepest level, the speed of light is defined as being about causality, and the fastest rate of causality that we're going to be able to measure in our laboratory frame between two interacting places in space-time. But photons are what's carrying the influence. What's this all seem like to the photon? So let me remind you about another diagram that we talked about last time, and it's this one. This is the basis of spectroscopy, this diagram. What you see there is some quantum system. I'm calling it the ground state. And I'm just drawing it the way chemists and some physicists would. Let's think about an electron in some available quantum level in an atom or a molecule. And then along comes a photon, HF, Planck's constant times frequency, and deposits a blat of energy and pumps that electron up to a different available quantum state, creates something we call an excited state. So that's the idea behind a lot of different forms of spectroscopy that we do in a modern scientific laboratory, but it's also the basis of seeing and of perception. Because think about being out under the stars and looking up at a star someplace. What's happening there? Well, turns out that what's happening is that there is an excited state of some kind on a star, say a rapidly vibrating atom or a dipole. That just means a charge separation that's holding some energy. What takes place is that energy gap, that piece of energy held by that oscillator, whatever it is out there as far away as a star or another galaxy, is letting go of its energy, and that perturbation is coming through space and time all the way to your eye, and it's hitting something that we refer to as a chromophore. That just means an absorbing species in the back of your eye that happens to be attached to a beautiful and intricately evolved photo sensing machinery. We call these things the visual pigments, and there's 3 of them in the back of our eye that can encode for red, green, and blue. And depending on what you read, it takes anywhere but like on the order of 4 photons, I think, to at least most of the time generate a visible signal for the most highly trained of people who sit down and look at stuff. Usually it takes a lot of photons to really see something happen, but it's an integration over, a sum over a whole bunch of discrete events, which is a train of photons hitting your eye. And the elemental event is that of one photon hitting one chromophore and creating an excited state, which then that energy gets relayed off by a protein machine, essentially, that is hooked into your nervous system, and boom, you see it. You get to see that star emitting photons so far away. Goes really deep. All right, let's think a little harder about what this means, because we just went through a derivation there with algebra and everything, suggesting that for photons, for that little traveling, whatever it is, there's no time. The clock rate has gone to 0, or at the very least it's undefinable. It's gone asymptotically smaller as things approach the speed of light. Well, light is going the speed of light. It's certainly reasonable to argue that photons experience no time. But wait a minute. Those stars are somewhere between hundreds and maybe a couple 100,000 even light years away. If you're out someplace that's really dark and really nice, and you know where to look, and you know how to look up and find the great square of Pegasus, and then find the constellation called Andromeda that spritz off of the great square of Pegasus a little bit towards the north. There's a star you can look at that's not a star. It's fuzzy. It's this little weird little splotch in the sky. A lot more obvious to see it if you look at it with binoculars. That is one of 2 naked eye observable galaxies outside of ours. The other one is actually quite close to it also. It's called the M33, the galaxy in Triangulum. In that case, you're looking millions of light years away. And so photons are boiling off of a star millions of light years away and somehow finding their way to the back of your eyeball and then into your brain, and you experience it. Well, from our laboratory frame, the way where we sit, there's a transit time that relates precisely to the distance between these objects and the speed of light, and you can compute it. And if it's 2 million light years away, as the Andromeda Galaxy is, then it took 2 million years for that light to come from that collection of stars into your eye. But the photons don't experience the time. As far as the photons are concerned, they're just a quantum state of excitation over there, going away, and then a new one comes into existence here. The photon was there, now it's here in your eye. No passage of time from the point of view of something traveling the speed of light. That's different. How do we accommodate that? How do we wrap our head around that? Well, you don't really. You just sort of get used to it and then try to work it into the rest of your scientific paradigm, the rest of your scientific structure. And you try to understand it and see where it's going to go. You can sort of hear a little bit of an echo of the ancient Greeks there, right? And so where we're going to be going with all this over the next time or two is now connecting up with a next level interpretation of quantum mechanics that sort of goes past what I have shared with folks at the Lodge over the last, 30 years since I've been coming there and every now and then talking about quantum mechanics and Schrodinger's cat and the mystery of measurement, the mystery of perception, nature of the universe, structure of space-time, how we are instantiated in it, how we operate, how we see, how we perceive. There's an interpretation of quantum mechanics that I really only started learning about in detail myself over the last couple of years. And it's called the transactional interpretation of quantum mechanics. Most recently, it is popularized by a really great speaker and author. I'm going to get a book right back. So if any of you want to read along and be ready for me next time I'm coming at you, there are some books that you could get your hands on. Probably the first one to read might be this. It's called Understanding Our Unseen Reality, Solving Quantum Riddles. And the author is Ruth Kastner. Very interesting thinker, and she really drives quantum mechanics into a beautiful area, and she's got a very strong philosophical sense. She does a great job connecting up complex ideas and a bunch of math with things that theosophists are going to like and resonate with. Next book of hers, Adventures in Quantum Land. It's a lot of overlap with that other book, but it's different. Actually, there's a reason to read both. And then the one I'm reading, and this gets a little bit more technical, it's called The Transactional Interpretation of Quantum Mechanics by Ruth Kastner. So we're going to be going into this over the next couple times. And what you're going to be hearing about is a view that brings together quantum mechanics and relativity in an important way. This is not the only approach that does that, but it's a good one. And I think it rounds out one's view of the universe and one's experience of oneself and the flow of time in a way that I believe is particularly pleasing and important. So if you feel like going out and getting those books, they're readily available around. And I would also mention this, which is that there's a great YouTube channel that is operated by a really far out guy who I enjoy quite a bit. His name is Jeffrey Mishlove. And gosh, I've been listening to Jeffrey Mishlove for the last 30 years. Because for a long time, like in the 80s and 90s, he had a radio program called Thinking Aloud. And in the last several years, it has come back in the form of a YouTube channel called New Thinking Aloud. And Ruth Kastner has been on Jeffrey Mislove's YouTube channel a number of times, and she does a great job there of explaining her own rendition of the transactional theory of quantum mechanics, or the transactional interpretation of quantum mechanics. It grows out of work by a fellow named Kramers that was done in the mid-80s, which actually grows out of work done by Einstein way back, when he realized that there was work to be done understanding the nature of absorption and emission of light. So this idea of a quantum ground state being promoted to an excited state by impingement of a photon, he realized there were things to be probed and learned at a deeper level about that than the way I just said it. That has now flowered fully in the form of something called absorber theory. And this underlies the transactional interpretation of quantum mechanics, and it's going to involve letting go of the idea of simply forward causality. The key empowering notion here is that quantum objects that are exchanging these photons, whatever they are, the influences are going back and forth, both forward in time and backward in time. And that ends up being the empowering key to unlocking a whole new level of thinking about and understanding all this stuff. And so I'm going to do my best to take us through that over the next couple sessions together. And hopefully we'll all feel a little different when we go out and look up at the stars after I finish with that. So I guess that's it for tonight. A little shorter than average, but I wish I was there to field some questions and talk with you all. Now you have a preview. You know where we're going to go. And you could also look back at a couple of my other talks where we did the relativity thing, because it's all going to be coming back and tied together, and we'll be going deeper with all of that. So I hope you're all doing well, and I will see you again in another 2 or 3 months. Good night.